Hey guys, this is Mrs. Mooney. We've been talking about linear systems of equations, and we know that some of these linear systems have exactly one solution when the lines intersect. And we also know that there are some special cases where we have no solution to a system of equations, or we have a system that has an infinite number of solutions or infinitely many solutions. So today I just want to bring all that together for you. If you could get out your note sheet that looks like this and follow along and take great notes. First, I want to take a look at sort of the normal case of two intersecting lines. And remember, if we have two straight lines, if they do intersect, they can only intersect in one location. Once they intersect, they're not going to double back on themselves and bump into each other again. So they will only ever have one solution. So in your notes, I want you to write exactly what I'm writing down or make sense of it for yourself. So now we want to ask, well, what does that look like in the equations in terms of the slope and the y-intercept? So if these two lines are going to intersect, they must have different slopes. So slopes are different. And it doesn't matter what the y-intercepts are. If the slopes are different, the lines will intersect. Even if they're just a little bit different, eventually they will bump into each other. What does that look like for their equations? So we may have y equals 3x plus 1 and y equals negative 2x plus 8. So we have a slope of 3 and a slope of negative 2. As long as those are different, our lines will intersect. So what you want to do in this case, if you're trying to compare two equations and figure out what type of solution you're looking at, you need to put these lines in slope-intercept form so that you can see what their slopes are. And we know what this looks like when we graph the two equations. We know that we'll see them intersect at this one point. But what does it look like when we solve the equations algebraically? So if we were to solve using substitution here, we would come up with x is equal to some number, and then we'd plug that back into one of the original equations, and we'd come up with y is equal to some number when x is equal to the number that we got for x. So we'd have an ordered pair x, y. This is what it looks like when we have a normal system of equations with one solution. The next type of system we want to look at is a system of two parallel lines. So we ask ourselves, what does it mean to be a solution to a system of equations? Well, it means the number of shared points for those two lines. So how many points can two parallel lines share? Or said another way, in how many places will two parallel lines intersect? Well, the very definition of parallel lines is that they never intersect. So these lines will share no solutions. They will never intersect. And what does that look like in terms of their slope and their y-intercept? Well, two parallel lines, we know they have to have the same exact slope. But in addition to the same slope, they must have different y-intercepts. If they had the same slope and the same y-intercept, it would be the same line. And we'll look at that in the next case down below. So their equations are going to look like y equals 2x plus 1 or y equals 2x plus 8. So notice that we have the same slopes, but we have different y-intercepts. So as long as if the slopes are the same, these numbers could be anything as long as they're different. And what does that look like when we're solving algebraically? Well, if we solve a system of parallel lines algebraically, we're going to get some crazy, untrue statement like 0 equals 8 or negative 1 equals 1. When you get an answer like this, it's a huge indicator that you're dealing with two parallel lines, a system of two parallel lines, and that you will have no solution. To double check, you want to put both of your equations into slope-intercept form and verify, am I in fact dealing with two lines with the same slope and different y-intercepts? And the third type of system that we might run into is a situation where we have the same line. It can also be thought of as two different lines that are coinciding, or two lines lying right on top of each other. So again, a solution to a system is the number of points that the two different lines share. So how many points would these lines share? Well, this blue line has an infinite number of solutions, and this yellow line also has an infinite number of solutions, and they all happen to be the same solutions. So these lines share all their solutions, or infinitely many solutions. And what does that look like in terms of the slope and the y-intercept? Well, again, the slopes are going to be the same. And because this is really just the same line, the y-intercepts will also be the same. So we're looking at, for example, something like y equals 1/2 x plus 3 and y equals 1/2 x plus 3. But it's not always this easy. It's not always given to us in these nice slope-intercept forms. So you may get something that looks like negative 1/2 x plus y equals 3 as your second line. So before you decide that these are not the same line, make sure you put it back into slope-intercept form. And then you can see that they are, in fact, the same line. When we solve these kinds of equations algebraically, we don't get nice x equals some number and y equals some number, and we don't get some crazy untrue statement like 0 equals 8. What we do get is a nice true statement that like 1 equals 1 or x equals x. When you get something like this when solving algebraically, that's a huge hint that you're dealing with infinitely many solutions. At that point, you want to make sure you're putting both of your equations into slope-intercept form and verifying that you do in fact have two copies of the same line. This is a great review of everything that we've learned thus far about the different types of linear systems of equations. So I hope you took good notes. If you missed anything, rewatch this video on YouTube so you can slow it down or even speed it up and fast forward as you need to. Make note of any questions that you have for me, and I will see you in class.